right, looks like this time it worked better. Maybe. Let's see if the YouTube. All right, seems to work. Can somebody say in chat something around like, is the stream working? Can you hear me all right? And things like that. Does the chat work? All right, cool. Thank you. So we are starting now. So what are we doing today? Some work that I'm doing on the 3D model compression loading requires me to write some amount of WebAssembly code. And so I had, like a week ago or so, I've added some new code that improves compression ratio. And I had to write a function that decompresses some data, or not quite decompresses, but like, let's say, adjusts some data so that the data can be compressed better. And so I have a scalar variant of this function, and the scalar variant is probably a bit slow, so I wanted to convert it to SIMD using WebAssembly. And I thought, well, why not do this on stream? Because, hey, maybe somebody will learn something, and maybe this will be entertaining. Word of warning, CMD in WebAssembly is a bleeding edge technology, meaning Chrome sort of supports it now if you enable this. Some opcodes are not implemented yet, some opcodes are implemented, but maybe they have bugs. Who knows what we'll run into. When I did my previous CMD work on WebAssembly, I had to use the beta version of Chrome. Now we'll try to use the stable version of Chrome and see how it goes. So we may run into issues along the way. So just a brief kind of glimpse into what we are doing today. We are taking a, 10-line C function, right? And we will try to convert it to WebAssembly SIMD. But first I'll have to write a tiny bit of code that actually measures performance of our code in the browser. And then there's a couple of other things I want to look at. So what is the thing we are optimizing today, or simplifying? The idea is as follows. So there is the file with the model with the mesh data. It uses GLTF, so let's say it's a GLB file. And GLB file has streams with different types of data. So there is position. Great. My ability to write text today is not working very well. Then there is normal, text code, and stuff like that. We will be using a model that's a very large model. It's like 6 million triangles or so, that has these 3 streams. Now, what happens then is that these streams are encoded using meshoptimizer's codec format in the GLB file. And then when the browser loads them, there is code that implements meshopt compression, or rather decompression, to decompress them into actual data, right? Like with actual positions and normals and texture coordinates. Now, in a perfect world, the codecs are designed for kind of really careful data layout, in the sense that, like, if you are storing a normal, you shouldn't store 3 components of the normal, just 2 components are enough. You can use the fantastic octahedral normal encoding for that. But GLTF doesn't support that. So for GLTF, the way I store normals is just 3 components, right? And I want to store 1 byte per component, so the way normals are stored is just X, 8-bit, Y, Z, and then 0, right? And for tangent data, it's the same. We are not dealing with tangents right now, but for tangent data it's the same, except that instead of 0, GLTF says it could be plus or minus 1 depending on whether you want the tangent frame to be right-handed or left-handed. Cool. So what's the issue? The issue goes like this, and we'll actually run GLTF back kind of like before and after to. Oh, let me open the model actually first so that we can look at the model. So I've checked out my branch in like a separate folder so that I don't mess anything up, and I've compiled a bunch of things. Please let me know if the text is not readable on screen. I tried to make it a bit larger to accommodate for possible video codec issues. So let's do this again. So we are working with a model that we are loading from an OBJ file, which takes a while because it's like 4 GB OBJ file or something like that, and converting it to a GLB file. And we see there's 3 streams: position, normal, texture coordinate, and then they compress to a certain number of bits per component after all that's said and done. So this is using the better compression that we are going to optimize today. But let's first see if this is even loadable in the browser. Please use a keyframe frequency of 4 seconds or less. Okay. Cute. I mean, all right. I don't know what to do about this. Keyframes are not being sent often enough. Okay. On the preview, it seems like things work, kind of. So oh, okay, now it's healthy, and now it's not. All right. I'm gonna hope that this is all mostly fine. I could like change video encoding settings or something, but I'm worried that if I do this, it'll cut the stream, and then I can't merge the stream back, and then there's 2 stream links again, and it's all terrible. So, I'm just gonna assume it's fine. So, let's try to load. Oh, I should remove my benchmarking code. Hold on. I've hacked some code just now to give us some performance data. And I should embed the textures so that I don't have to deal with texture files. All right, let's try this again. Oh, and now I should, for all of this, I'm usually using a simple viewing like program that uses 3GS and stuff, but I didn't like, okay, hold on. Oh, I could steal, I already did this here. There's like some camera setup that's needed for this model that I forgot about. Okay. Okay, close enough. Okay. I should write some code that actually fits the model on screen properly once and then not have to deal with this again. Why is it misaligned in the bidirection? Okay, all right, with the process of trial and error, we have actually loaded the model. Great. So this is the model that we are working with, and I think I have gamma issues again. Hold on. All right, so this is the actual model that we're working with. It's a 3D scan of the Nefertiti bust from some German university that I forgot about. It's a good, really high poly model, right? That's all it is. All right, yeah, stream is looking fine. Yeah, that's what I thought. Next time, I think I'm actually recording at like 1440p or something instead of 1080p. So maybe next time I'll just set it to 1080p. And also maybe I should have disabled the VPN because maybe that clamps the bandwidth somehow. Anyway, whatever. So point is, this is the model. It's like 6 million triangles, 3 point something, 6.4 million triangles, 3.4 roughly million vertices, and it takes 16 meg with compression and things like that. Before gzip, it takes 16 megabytes of vertex data and like 7 megabytes of index data. So this is with the code that we want to optimize running already. So let me first disable this fancy stuff that I was doing with normals and then talk about what it actually does. So I guess I can just do this and then so I'll now recompress the model to kind of how the model used to be, and then we'll actually measure performance in that scenario, and then we'll see. Right, so I disabled some code, and this now I'm actually outputting the full 3-component normal, what I was talking about before. And you see it takes 15 bits per each normal, and it takes 10.5 bits like if we do the special stuff, which is actually really simple. Now the model still looks fine. So what is the code that I've added to it? The code is very, very simple. The code says, okay, so you have a 3-component normal, but the components are linked together, right? There's dependencies between them in the sense that the normal is unit length, so the sum of squares of components is 1, which means that we can reconstruct the modulo of one of the components, like z component, from the rest. Minus. Now, of course, this doesn't give us the sign of z. Z can be positive or negative. Remember, this is a normal. This is the vertex normal, so it's stored in object space, which means it could be positive or negative, which means we need to store the sign, but we don't need to store the magnitude. And so this is what the code is doing. Like the reason why we are able to save a few bits, like 5 bits or whatever, per normal is because instead of encoding 3 components, we are encoding 2 components and the sign of the 3rd component, and then we are reconstructing the sign. Now, normally you would do this kind of stuff using shaders. For example, you would encode 2 components in the sign, or you would use octahedral encoding, and then in the shader you would reconstruct the normal, and it's actually pretty cheap. But what I'm working on is GLTF support, and for GLTF you kind of have to assume that the viewer doesn't know about this special normal encodings and things like that, and just works with plain old normals. So we have to do this reconstruction ourselves before we hand off data to the renderer. And this is what we are going to be doing, so this is exactly what the function does. Now we can look at this C code. Let me make sure. Yeah, so there's like several variants of this because I also need this for 4-component vectors because quaternions are also unit length and they're encoded for animation data. And then I need this for kind of 1 byte per component and 2 bytes per component for different precision variants. But we are just going to be looking at this loop today. So we go over all vertices, we take x and y components of the normal. They are stored in bytes, so we convert them to floats between -1 and 1. Like the original byte is between -127 and +127, so we divide by 127. And then we reconstruct the absolute value of z. or rather the square of the absolute value of z. Then we take the square root. Note that we have to be really careful here because like in a perfect world, the normal is exactly unit length, so the math that I showed there works. In an imperfect world, there are errors in x and y, and so this expression can actually be negative. And so when it's negative, obviously the square root doesn't really work. It's not very happy. It will produce nans. So what we have to do is we have to clamp this to 0, and then we have to take the square root, and then we are working with the stream of bytes, right? Not the stream of floats. So then we have to take the square root and re-encode it as a byte value. And this is still a positive value, like it doesn't have the sign. And then we say, well, we need to read the sign from somewhere, so we'll read the sign from where the original z component was, because that's where the encoder will store it. And then we'll just, if the sign is 1, we'll just negate the module, right? And then if it's 0, then we'll just keep it as is, and then we'll store it back. So this is what this does. This is pretty simple, and this saves an appreciable amount of data on normals. Like, it may not seem that much, but so this brings us from like roughly 30, like it's like basically 5 bits out of 40 or something like this. So it's more than 10% of the vertex, and actually the savings I think are slightly more after gzip. So it's pretty good for hopefully relatively minimum amount of processing. But now let's actually look at how much it costs us to decompress this. In this output, this is, if you look at this function, it's called filter, because it filters the decompressed data after the fact. So this is what this filter refers to. So you see here we have 3 streams in this original model, 3 streams that don't have any filter. And then if I am gonna undo my hack and recompress the model again, then we will see that the filter is actually defined to something for one of the streams, which is the normal stream. So this is the normal stream, and this is what we're going to optimize. Now, right now, all of these numbers feel pretty low. Like, we are decoding data at like 200 to 400 megabytes per second. Now, and this is just one run of the function. This is what the code I had here was doing, where maybe we want to run this like 5 times and then just have more data points, right? Okay. So here we can see that it takes us a while actually to decompress the filtered stream. Like it runs at 240 megabytes a second or something, and then the other streams are faster, they run at like 400. So this is probably the cost of our filter function, but our filter function is really naive right now. Important point of note though, we are not running SIMD code. Like in my actual decoder, the parts that aren't using this filter are actually optimized using SIMD already, and the thing that's not optimized is this filter function. So what we are gonna do is we are gonna enable SIMD. As I mentioned, it's kind of bleeding edge, so you have to enable this in browser, and then I guess you have to restart the browser. Okay. Let's reload the stream website. Okay. So, oh great, and it doesn't work. Okay. Let's try in Chrome Canary. This is odd. I thought it all worked. Okay, that's gonna be great. This is gonna be a very short stream if our CMD stuff doesn't really work. Let's try to figure out what's been going on here. Is this the latest? Now I'm worried that the latest Chrome broke Uh, all right, so what doesn't work is the thing that we have just compiled. Oh, great. Let's see here. I didn't expect this. Let's try to... I'm hoping that the issue is in the new functions. It's gonna be a bit of a pain, but I'm hoping that the issue is here, because then I know what we are gonna do about this. Oh, right. So I'm using mscripton to compile my C code into the WebAssembly code. Okay, great. So this is, so let me explain what's happening because it's kind of interesting. So what's happening here, what seems like it's happening here, and we can confirm this, is that even though I'm not using any CMD code in these functions, Clang helpfully says, well, your code looks vectorizable to me. Let me like help you by vectorizing the code. But then when it does so, it produces functions that, like instructions that Chrome doesn't recognize. And it's probably because Chrome hasn't implemented them yet. I know of a couple of cases like this where Chrome just doesn't like certain instructions in WebAssembly. So we're gonna have to work through that. But oh, and also what you see is that once we enabled CMD, we're actually running much faster. It's like 1+ gigabytes a second for all streams, but of course we disabled the normal filtering. So let's try to disable automatic vectorization in Clang. Oh, also let me check if, okay, so I don't have to be using Chrome Canary, it's just that, no vectorize. This is actually even better because it's sort of good that we have to do this, because this means that we'll compare this with kind of like actually scalar code. It also means that it's possible that in the future, at some point when all of this ecosystem works beautifully, I wouldn't actually have had to have done the thing I'm gonna do right now, as in like if the compiler vectorizes this function, maybe it does a perfect job at this, who knows. But historically, compiler hasn't done a perfect job at vectorizing, so I'm not expecting miracles here. Interesting. Even disabling vectorization somehow didn't help. This is most curious. Is that the right keyword? So that's a difference. Okay. Oh, what? Maybe I also didn't, like, browsers sometimes cache data, so maybe no. Shift to 5, okay. Interesting. So disabling vectorization doesn't help, which is annoying. So it might be some other kind of code generation difference that I'm running into here. Let me confirm again that like disabling this makes it work. Oh, maybe I didn't have to do this for both functions actually. Let's try this. So the only loop that I need right now is the loop that we have already looked at. So let me try to do this. Oh. Am I doing this in the right? Yeah, okay. the offset changed. It's also pretty annoying that Chrome doesn't tell you like which instruction's wrong. Let's triple confirm that this is actually our loop. I'm wondering why. Oh, I think there might be. Yeah. Is there any other way in Clang to disable? It's clearly generating CMD instructions in the function that I'm trying to optimize, and it's clearly doing that wrong. But I'm not sure why. Can we wasm obj dump? We can definitely wasm obj dump and see what's going on here. Let's try to do that. So let me just keep the loop here, because this is what I need. Oh, also one minor point of note. So this is not loading. Let me change. So as you see, as you probably saw when I was disabling this function, like the rendering of the model still looked pretty reasonable. This is because it's hard to look at the normal data here without actually displaying the normal data directly. So let me very briefly fix that. So I'll disable SIMD loading for a second so that we're all good. Now I will change. I have this snippet that shows the normals. All right, so this is the actual normal output, and then we'll actually have to make sure that it's the same. And as you can see here, the mesh is clearly very detailed because there's a lot of variance in the normal date, even though there's no normal map here. All right. So, so the issue is that Chrome doesn't load the CMD blob. I think I have some. Hold on. Okay. Weird. So let's first see which function Chrome is complaining about. So it's complaining about function number 8, and it's complaining about the offset 2663, and this is going to be potentially hard to fish out of that in the CMD blob. So function number 8, I mean, it's definitely our function. There's no names for these functions because they aren't exported. We can export it, but it's our function, all right? So is it -s, -d? Decoder CMDs, decoder CMDs. So let me just scan this. Aha. Beautiful. So even though, oh yeah, so this is actually trying to use CMD with extract lane and stuff, right? So this doesn't work. I'm pretty sure it's v128 const because I've ran into this issue so many times now. Let's try to see if this is right. So the offset here is 2663, and then it's A67, and then at A67 we have v128 const. So that's great. Yeah, so the instruction is v128 const. This is a beautiful problem because Chrome doesn't support it. Chrome hasn't supported this for a while. My understanding is it's hard to support it in Chrome, like they'll have to do this because this is part of the spec, but it's hard to support it because their code generator right now doesn't support efficient kind of constant embedding, which in my opinion, is a big issue that they'll have to fix no matter what for other reasons. But so the thing I want to know is why did disabling... So what happens here is the compiler tried to vectorize this. I don't particularly like the way it vectorizes this. I think we are gonna do a better job looking at this. Maybe I'm wrong. It's hard to know because this code doesn't like run, right? Like it kept the division. Isn't there fast math implied? Anyway, like I don't like this code anyway, but also this code doesn't load in Chrome. So what I'm curious about is why did disabling vectorization not help? So let's try to do this again. Where were we? So compile the JavaScript blobs, disassemble again, look at the disassembly again. Yeah. Oh. So when we disable vectorization, there's no actual vectorized code here. It's all floating point. But it still loads a constant. I think this is 127, probably. Does it sound right? It's probably 127. Or maybe not, I don't know. Floating point online decimal. All right. Oh, there's no single precision here. Oh, maybe this is single precision. Yeah, 127. So for some reason I don't even. This is odd. All right. Alright, this is annoying. I haven't run into this before. For some reason it uses vectorized constants to store these scalars. Yeah, I don't know why it's doing that. That's kind of odd. And like I think I can maybe disable this somehow, but let's just pessimize this code gen in hopes that it will. Like the only reason why I even need a scalar function is it would be nice to be able to like actually compare performance with that. Okay, so volatile helped, as volatiles usually do. We can hopefully like work now. All right. So this was awkward, but whatever. Well, no, yeah, yeah. Well, so I can't use CMD 128 because I actually need unimplemented CMD opcodes that are actually implemented in Chrome in other code. And I'm not sure. I think we're gonna try to use widening loads today that probably are also unimplemented, and hopefully Chrome implements them. So I think I actually need unimplemented CMD. Yeah, I'm not clear why the vectorized instructions were emitted here in the first place, because it doesn't seem like advantageous for code gen, but whatever. All right, so we are back on track. I warned you guys that it's so bleeding edge. But we are back on track in that we have a model that has normal stream, and it's running our function, and our function is running pretty slow. So just as a kind of baseline benchmark, right? So we are running at like 440 megabytes a second, roughly speaking. And this is with the meshoptimizer decoding that's relatively involved, because it's not like involved in the sense that it actually is very fast, but it uses tricky SIMD instructions, it uses bytes instead of floats, stuff like that. And you can clearly see that in other streams we are reaching 1+ gigabytes a second, but here we aren't. And so this is all because of our scalar filter function, presumably. I don't think volatile actually makes that big of a difference here performance-wise. It's just I had to use it because maybe it will be faster if I do this, but it's all kind of like whatever, it doesn't matter. So if I disable filtering completely, the normals are going to be broken, presumably, right? So clearly we actually need this code to run, but we are running at 1+ gigabytes a second. Now filtering has to have a cost, but I'm hoping that the cost isn't as big as to drop us from 1.2 to like 400 something, 1.2 gigabytes to 400 something megabytes a second. So, all right. Now let's actually do SIMD. So let me back up. I know the code that I want to write. Now clearly we may run into some further issues with the instructions and stuff like that, but we'll see. So our input is chunks of 4 bytes laid out sequentially. So it's like X, Y, Z, something. X, Y, let's call it S, because it's like a sign of the Z value, as I said before. X, Y, S, something, etc. Right? And so each chunk is 4 bytes. And so what we need to do is we need to change the signs of the Z value to the square root of the like 1 minus X squared minus Y squared, etc. To use SIMD efficiently, we have to work on groups of values. For example, we want to compute the square root for 4 values at a time. WASM SIMD, for people who might be familiar with other SIMD instruction sets, WASM SIMD is always 4 instructions at a time. So there's an instruction that computes the square root of the vector by effectively saying x is square root of x, y is square root of y, z is square root of z, w is square root of w, if you think of the lanes of the vector as being labeled as x, y, z, w. Now, so for us to compute 4 square roots at a time, we need to work on 4 normals at a time, right? So we're going to work on 4 normals at a time. So this means that we need to load 4 normals worth of data, which is 4 times 4 bytes or 16 bytes, into registers. But then what we have to do is we have to transpose them. So if I look at the normal stream as okay, I don't usually work with whiteboard. I usually work with OneNote, so I don't know how to copy stuff, but like whatever. So this is how the sort of vertical layout of the stream looks like if you think of each row as taking 4 bytes, right? So what we want to do is we want to have one vector that has all x's, so a column vector, one vector that has all y's, all signs, etc. And then we can do things like square all x's with one instruction, square all y's, square root, etc. So what we'll need to do is we'll need to transpose. There is common primitives for transpose that involve shuffles. Let me see. Is this already what I need? Hold on. This doesn't look right. This is oh yeah, right. This is an 8-bit transpose that transposes. So we'll need to write a transpose function, which will have to do some shuffles. But everything else will be pretty straightforward. Now, when we load the values, we could load one vector worth of data, which is 4 bytes per normal, right? So altogether, this is 16 bytes worth of data. And then we could like extract things from that vector, but that may not be a good idea. So let me first look at the spec. So there's two ways to deal with things like this, where you have a vector that has 8-bit values, effectively in our case, right? And what we want to do is we want to convert, like if we look at the code, at the C code. So what does this line do? It says there's this value, which is an 8-bit integer, assigned 8-bit integer. And then it wants to convert it to a float, right? But I don't think the CMD spec in WebAssembly has this kind of instruction for sure, right? It has an instruction that converts a 32-bit integer to a float. So what we need to do is we need to first expand the 8-bit integer into the 32-bit one, and then we need to cast it to a float, right? So these are two separate instructions. Now, this one is simple. There's just an instruction that converts integer to floating point. Done. Like all integers that we are dealing with are small, so we don't really care about what happens in this case. This is surprisingly imprecise for a WebAssembly spec. I thought it would be like precise, I guess, about what's happening for integers that aren't integers that are too large to fit in a float precisely, but whatever. So we need to look into this, right? There's two options for this. One is this integer to integer widening, which, let's see. Oh, interesting. Which will have to run in two phases. One is widen the 8-bit integer into the 16-bit, and then the other one is to widen the 16-bit into the 32-bit. And the other option is, there were loads somewhere. Yeah, these guys. Like, so there's an option to load, hold on. Oh, it's the same. It's also two-step. Okay. I thought there would be an instruction that like loads 4 8-bit values and just extend this to 32-bit, but it doesn't seem to be the case. Okay, so we have two options. One is we can do a load from memory using widening, and one is we can just widen using these guys. These guys. And so I don't know which is supported by Chrome, but I guess we're gonna find out. And then we'll need the transpose, and then everything else is pretty simple. So how are we gonna go about this? Oh, one thing I should note is there's no debugger for any of this, right? So if something goes wrong, we're gonna have to debug this code a bit manually. The way you do this is by doing Printf Debugging, right? There's nothing else. But of course you don't have an actual printf, so if our code doesn't work from the first try, then we'll have to get creative. So, one final point before I start actually writing some code. So I said that we are going to process normals in groups of 4. However, what happens if there's 3 normals in the input buffer? One way to look at this is, well, we're just going to run this scalar code after the vector code to process the last like 1, 2, or 3 normals. The other way to look at this is the way the filter is actually used from my decoder, I think, and let me confirm this. I don't have, okay, cool. I don't have time to go into like how the decoder actually works, so just assume it's a black box that calls the filter sometimes. So the way the decoder works internally though is that processes vertices in aligned blocks, aligned to 16 vertices worth of data. And so what we actually will do for the time being is that we'll say, well, the filter is only ever called on blocks with aligned number of vertices. and this will simplify our efforts a bit. Certs are compiled out of WebAssembly codes, so I can't even like know if this is true, but let's just assume it's true. And then we're gonna have, well, I have this macro SIMD wasm, which says, hey, you're compiling in a WebAssembly environment that has SIMD enabled. So we're gonna use that. I'm kind of worried that I will write some code and then Chrome will just refuse to load this, but it took me quite a while. So like there's already a bunch of CMD WebAssembly code in this file that does the actual decoding, which is why the decoding is so fast. It took me a while to kind of find the optimal balance between here's the code like that runs fast and Chrome can load versus here's a code that I think may be slightly faster but Chrome can't load yet. Hopefully all of these things will be resolved eventually once Chrome gets full support for the spec. For now, I mean, I think it's reasonable. Like, a lot of the stuff is so in flux that Chrome right now has support for some instructions that are not part of the spec yet. Because, I mean, if you don't know if an instruction is beneficial, you don't know if you should include it in the spec. Because there's a temptation to include everything that you could possibly want in the spec. But then if you how are you going to know if the instruction is beneficial without implementing it, right? In fact, I got involved in this process pretty early, fortunately for me, because there was an instruction that my CMD decoder just wasn't possible without, that wasn't part of the spec at some point early on, and now it is. And now I can use it in Chrome. Anyway, so let's just try to write code that does this reasonably optimally, and then if it doesn't work, we'll have to do something about if Chrome doesn't load it, we'll have to do something about this. Maybe Chrome loads it, but the code has bugs. So we'll process vertices in groups of 4, and then each group is 4 bytes, so the total is 16 bytes. So we need to load the 16 bytes into a vector. I'm gonna use the only thing you can use really, which is wasm SIMD 128 header. That's part of Unscripton. It's really good in the sense that like the instructions, the intrinsics usually have human readable, human understandable names, unlike some other instructions in SSE, for example. And there is only a single type of a vector. So it's not like Neon where there is a type for each. Like there's a vector type for each scalar type that you're storing within the vector, which it seems like a good idea if you like types to say, hey, 16 8-bit integers is a different type from 4 floats. But actually when you're writing CMD code, the extra type safety gets in the way so much that it's much more productive to actually just not have types. At least this is my experience with basically all other instruction sets and intrinsics that I've used. So to load stuff, you use wasm v128 load, so we're going to use that. Oh, also the vector type v128 is probably the shortest one that I've ever seen in all other instruction sets, which is also great. So this is going to be our 4 normals. No. Wait. Why is there times 4? Alright, yes. Yeah. So this is the offset to the first normal, so we're gonna load all of them. Then we need to expand them. So this data right now is laid out like this: x, y, z, or like the sign of z, and then 0. Let's say we don't really care about this 0 for normals, but we need to preserve it for tangents. So I'm assuming there's also narrowing here, right? That works the same way. Narrow from 32 to 16, and then from. It's unfortunate there's no like single step narrow, but I guess SSE doesn't have it either. I would assume, so maybe it's fine. So the way we are going to do this, I think, is like this. There is a widening instruction that goes from 8-bit to 16-bit integers, and there is two of them because one of them does, I think, low half of the smaller lane vector. So one of them presumably takes the first 8 bytes of the vector and then expands them to like 16-bit. And this is our two normals. So naming things in CMD is always a challenge. Let's just say that the first two normals as 16-bit integers. Oh, and I don't know what the... Yeah. So this guy widens from 16 8-bit integers to 8 16-bit integers. And then we'll need the same thing to widen the high half. So this widens the first 8 bytes, which is the first two normals. This widens the second 8 bytes, which is the second two normals. And now here and here we have 8 values, and each value is 16 bits, and we want 4 values, and each value is 32 bits. So we'll need more widening to do. And this is gonna be that. Oh, I'm surprised. Actually, wait, why is widening? Oh, there's only signed variants of this. Oh, right, yes, this is how the sign is determined. Never mind, it's all good. We probably want, yeah, all our numbers are signed, so we want sign widening. All right, so now we want this guy, basically. Zero, 1. All right, so presumably now we have 4 vectors, and then each vector has a 32-bit integer, like 4 32-bit integers that correspond to the normal components, so x, y, z, and then something else. So now we need to transpose. I don't like writing the transpose function myself. What I would do here is that I would find an SSE2 transpose, and then just map it directly to CMD code. Oh, actually, I can do, I think the way this works is, oh dear. Okay. No, this is gonna be painful. Like, my goal is not just to write, oh, actually, let's, can we punt on this somehow? No, it's gonna be hard. We need to transpose. So the thing is, I want to transpose, and I want to transpose 4 vectors into 4 other vectors. The issue is I don't just want to transpose, I want to transpose that's efficient. And so transposes that are efficient tend to be transposes that compile kind of one-to-one into SSE code. And is the stream working? Okay, good. And SSE has a very constrained set of instructions that move data between different vectors. And WASM has a very unconstrained instructions. Like, there's one instruction that implements a general byte transpose that says, for the target vector, can you pull this byte from there, this byte from there, etc., etc., etc. But the issue is, of course, when you compile this instruction to the actual hardware, if the hardware doesn't support a general purpose shuffle, and Intel's hardware sort of does now, but not quite, not in the same way, and also Chrome doesn't like to generate this because reasons. So really I need a shuffle, oh sorry, a transpose that can be efficiently compiled towards SSE. But okay, there's no kind of this is a beautiful illustration of what I need to do. So you see I have 4 vectors with x, y, z, and w, and I want 4 vectors with x's, y's, z's, and w's. I think this instruction is implemented in terms of like a wrong shuffle instruction, but maybe I should just do this. Alright, this is the unfavorite part of this because the only thing I don't like about dealing with SIMD stuff is transposes. They tend to be painful to write. They're not like too painful to write, but it's like easy to get them wrong, and then they're different on different architectures. So I thought I would try to just steal one from SSE and then kind of recompile it to WASM, but maybe I'll just have to write one. Maybe it's not that bad. Am I even looking in the right place? Yeah. Alright, great. Oh, yeah. Okay. Right. So this is kind of what I want. I want a WASM instruction sequence that compiles into 8 shuffles, 8 SSE shuffles. All right, well, let's just do this. Like, I don't think there is a particularly nice way of doing this, so let's just add a function that takes if any part of this code doesn't work, it's going to be the transpose function. So it takes 4 vectors and then shuffles them so that rows become columns and vice versa. And the way we're going to do this is we're going to start with the Intel version of this, and then we're going to decipher this, I guess. Because this guy is just a primitive for general purpose shuffling of 4 component vectors. Oh, and we're actually no, not like this. I have some macros here that simplify the job of me writing WASM code here a bit. Like, it's really kind of painful to write sequences like this, right, that reorder individual bytes, because often what you want to reorder is not bytes, it's some high-level components like and these map exactly one-to-one to SSE, and I didn't check if Chrome actually does this, but like in theory it could. So I guess what I could do, and this is terribly named, it should probably be like Swizzle. So I guess what I could do is I could implement an SSE-like shuffle instruction that takes 2 vectors, like A and B, and to be less obnoxious about this. Oh, but no, yeah, that's fine. And 4 indices, and then the way SSE shuffles work is like this. let me switch back to this. So the way SSE shuffles work is roughly like this. You have two vectors, A and B, and you have four indices, I, J, K, L, let's say. These four indices are packed into one byte, which is why in SSE code you see this like X44. What does this mean? Well, this means it's a byte that has four 2-bit indices. So all of these are from 0 to 3, right? So each one indicates a specific component in the vector that you're trying to get. But, and there is 4 of them, right? But I and J always refer to the components of A, and K and L always refer to the components of B. So it's a shuffle that says, hey, given 2 vectors, let me reorder the 4-byte, like the float basically, or integer values inside these vectors as follows. For example, you can say I want a.x, a.y, b.z, b.w. And the way you do this is I is x, so it's 0, j is 1, k is 2, l is 3, right? But note that the first 2 output components are always referring to A, and the second 2 are always referring to B. So you can't, with one shuffle instruction, say, in SSE, say a.x, b.y, like a.z, b.w. So it's less general than that. But turns out that for transposes, it's enough to use the simpler instruction, because it transposes require you to use 8 vector operations no matter what, at least using the basic SSE and in Neon and like same thing. I think in every instruction set that I've seen, you basically need 8 operations, unless you have some really general high-level primitive like transpose things in these 4 vectors somehow. I'm not sure how that would work. So what I'm gonna do is I'm gonna implement a macro that basically is identical to the shuffle macro, but it's less obnoxious. So like it doesn't require you to specify these bit masks, and instead it's just 4 indices. And then we are gonna recode these shuffles into my WASM shuffles, and hopefully this will work. So the issue here is that I have to synthesize the kind of WASM compliant byte indices from my 4-byte indices. So for example, like the WASM shuffle instruction has 16 indices that you have to specify, and each index refers to a byte in one of the source 2 vectors, where 0 to 15 is the first and 16 to 31 is the second. So like for example, this guy says, hey, give me the last byte in the second vector. And this guy says, give me byte number 8 in the first vector, right? So basically what I have to do here is I have to take my indices that refer to the 4-byte values, convert them to byte indices, to 4-byte indices. So this is what this already does, right? But then for the second 2 output values, instead of using the first vector, I have to add 16 to use this second one. Oops. Okay. All right. Maybe this is right. Who knows? And now we are gonna do the transpose dance, which is we're gonna write the exact same code that this beautiful assembly macro has, right? Let's do it like this. And we'll have to change the magical byte values here into something meaningful. Now, in SSE, unfortunately, these bytes specify the output components in reverse, because SSE encoding is like really weird. But I think it's not gonna matter here. So Wait. I should have named this row 0, but too late for that. How's my... Yeah, okay. Alright, so to decipher these values, we just open the calculator and we say 44. What does this look like in binary? So in binary it looks like 0, 1, 1, 0, 1, 0, but because the SSC encoding is reversed, it's actually say as 0, 1, 0, 1. I don't know if any of this is actually true, but hey, we are gonna figure it out when we try to run the code. And then EE is 3232, but it's actually 2323, and then this is 0101. Now that it's written like this, it actually should be really easy to understand why the shuffle works, and I might show this later. So this is 0202, and this is 1313. This is like a lesson in kind of designing the intrinsics a bit. This is I type it here, right? This is so much easier to understand than the SSE variant, and it's so much easier to, like, if you expand this to WASM byte shuffles, it's going to be impossible for you to figure out what the hell this code is doing. And here it's actually pretty simple. I might show this, especially if we have to debug this code. We are pretty close to being able to run something. I think in like 10 minutes or so we will try to run something. So we'll see. So I'll go over the shuffles later if I have time and stuff like that. Alright, so now after transpose, each of these has 4 components like X, Y, Z, and W in them. Now we can actually start computing something. So for this, we need to say, well, to compute X, we need to take X, which is an N0. X is a float now. Sorry, is an integer, but it's a 32-bit integer. So we can use the convert intrinsic, this guy, to convert from integers to floats. Oh, it's actually 128T, isn't it? Haha. Is it? Yeah, okay. Damn it. I take back my comment about the shortest possible type that I've seen. It's slightly longer. Alright, so what are we doing? We are doing this. So this converts us from integers to floats. Then we are going to multiply, or we're going to divide by 127, but we're going to just multiply by the inverse. Believe it or not, I've never actually used floating point WASM SIMD. All of the SIMD work that I've done with WASM so far was with bytes and things like that, so I don't actually know how anything is called. So this, oops. So this multiplies by 1 over 127. This does the same for this D component. Now we need to, so this takes care of these two things. Now we need to compute this ZZ thingy, which is a square of the Z component, right? There is like this thing which does a multiply subtract. I forget which direction it goes in, if it's like A times B minus C or not, and in theory we could use that, but I'm pretty sure Chrome won't support any of that, so I'm just gonna stick to basics. splat. So we'll take 1 and we'll subtract I guess we're gonna subtract the sum of squares. So that's z. Now we need to clamp z. To clamp, we can use max instruction, hopefully. Yeah. Oh, wait. Yes. All right, good. And then we are going to use square root instruction. This one. So see, like this part was weird, right? Like this part was decidedly weird. But after this, I'm just basically taking each line of the code that I used to have that worked on 1 value and convert it to a line that uses SIMD intrinsics that works on 4 values at a time. This is a very, very general and useful vectorization technique that applies far beyond WASM or 4-component vectors or anything like that. I wrote about this a bit in my blog post from a few years back about optimizing slurp. If you are curious, you should look at this post and read it, because it talks about similar things to what we are doing right now, just in a different environment. Anyway, so all right, and now we need an integer that represents the square root that we have just computed as a 8-bit. Like we'll need a 32-bit integer that represents the encoding of this float into an 8-bit value, which is what this does, right? This is where multiply add is probably a much better fit, but whatever. So I'm assuming. Oh, let me just look it up. Yeah, okay. No, wait. That's not what I want. No. Okay, convert to integer towards 0. So this emulates the C rules, I guess. Yeah, which is good. All right, this one. Maybe I should extract the constants that I'm using in like separate values, because some of them might repeat, or actually most of them don't repeat, but I'm gonna hope that the compiler does something meaningful with this code. Wait. And the reason why I have to do 0.5 is to round. Alright, so this adds, so this does that. Now the final thing I need to do is I need to invert the sign of the value if the original value was 1. So this guy is the z component, which we don't have, of course, right? And it contains 1 if the value should be negated and 0 if the value should not be negated. And I haven't thought about what the best way is for me to do that yet. So I guess I'm gonna do that now. Like, I can do something stupid for now, I guess. So let me do something stupid, and I may come back to this. The stupid thing I'm gonna do is replicate this exactly. Like, to replicate this exactly, I will select, so I will build a mask that just compares this value, the z value, right, the sign of the z value rather to 0. And I have no idea how to do that. And then I'm just gonna select, there's like a bit select instruction that selects between two vectors, and I don't remember what the semantics are. I remember they were weird. They were like opposite from what I would expect. Yeah, it selects v1 when the mask is 1. So if the value is equal to 0, we don't have to do a sign flip. So we will just select the value, and if we do, we will need to negate it. There is a slightly faster way to do this, I think, using like bit operations, but let's just not do that for now. Alright, so at this point we have our x, y, z values, and we also have this n3 which we didn't touch. It's like the w, which we're gonna preserve as is. And then we need to convert them back. So to convert them back, we need to first transpose them back into the column row order, whichever. Fortunately, we just wrote a function that maybe works that does that. And then we need to output the results, but before we output the results, we need to put them back into the 8-bit. So like here, we did this 8 to 32-bit conversion, and then we have to do this again in reverse. Narrow. So the operation that goes from smaller bit counts to larger is called widen, and the reverse, of course, is called narrow. We need a narrow. We need to do this in 2 steps again, just as we did back there. What are we gonna call this? I don't know, let's call this R0, R01, I guess. So the names are slightly misleading here, I guess, because like these values, after this call, these values aren't x, y, z, and w. They are like the first normal, second normal, third normal, and fourth normal. But it's fine. Names are hard. And then we need to narrow further, probably with this one. Yeah. The way to read these instruction names is like this. Every WASM instruction, intrinsic, produces the result that is of type that is written first. And for those that have this, it consumes the type that is written last. So this guy says, hey, let me take 4 32-bit integers and narrow them to 8. Let me take 2 groups, like 2 vectors. Each one has 4 32-bit integers. In total, this is 8 32-bit integers. And narrow this to 1 vector with 8 16-bit integers. All right, and then finally, we can just store the result back. I'm going to be shocked if this code just works. But hey, who knows? So we've written code, we don't know if the code compiles, but if the code compiles and runs, then maybe it's faster. And let's check if it compiles first. Of course it doesn't. Hey, wait, what? Hold on. what is the type? Yeah, V128T. Oh, I see. When I implemented transpose 4, I was supposed to guard it with SIMD wasm, and I should probably move this thing. Yeah, I will move this somewhere. Okay, and 4. It's not called data, it's, oh right, I see. Names are hard. Damn it. Oh, okay, I know. I'm gonna, well, no. Okay, our code now compiles. Who knows if it runs? Who knows if it loads? I know nothing. Yeah. So there's 2 problems that we have. One problem is the code is not working clearly. The other problem is the code is slow. And the reason why I say that these are 2 problems is because, I mean, the code not working right doesn't surprise me too much, because clearly a lot of things could go wrong here. The code being slow is unfortunate, because when you work with CMD, it's usually is the case that, like, so you write a bunch of code like this, and then of course there's bugs somewhere, but you fix these bugs, and then the code runs, but the bugs are rarely performance bugs. So like, I feel pretty confident that we're gonna fix the bugs quickly. I feel less confident that we are gonna fix performance quickly, especially because I tried to get Chrome to output assembly last night for WASM, and it does this for WASM, but it doesn't do this for CMD WASM for my specific configuration for some reason. I'm not sure why. So this is gonna be painful to fix. But maybe the good news is, like, it's a good benchmark that somebody in V8 can improve later. I don't know. But okay, so let's deal with the correctness issue first. Clearly, this is like completely wrong, right? There's nothing right about this. So how are we gonna? So let me do this first. So let's compile a scalar code. And let me actually open it in a separate tab so that we can just tab back to like how this should work, right? So now in the scalar code, let me briefly change z back to 0. Not back to, like, the output z is always going to be 0 in scalar code. And the reason why I want to do this is because it's a very quick way to know, like, this is how the normals should work if the z component is 0. Now let me do the same thing in CMD code, and I'm gonna know if the bug is in the transposes that we are doing, or if the bug is in the actual math here, right? And then we can do debug prints and whatnot and narrow it down. So let's do this. Oops, yeah. Okay, so clearly the bug is not in our math, or maybe the bug is in our math, we don't know. But the bug is in the transposes or something, right? Because, oh no, wait, hold on. I'm not even doing, oh, wait, hold on. I was outputting the floating point, and this is where type safety could have been good, arguably. I was outputting the floating point, like the goal of this function is to compute the new value of z. The goal of this function is not to touch anything else. So I was accidentally outputting completely wrong things to the z. All right, so I mean, it's still broken. So this is interesting. This is really interesting. This seems to suggest that our transposes are broken or something. I wonder what low and high means exactly. I strongly suspect no, maybe not. All right, let's just do debug prints. Like, I don't see a better way to debug this than just printing what exactly goes wrong, right? Let's see if chat has any insightful comments. It doesn't. All right, so the performance problem bugs me a bit. Like, this code is slightly faster than this scalar code, but it's faster by like a fraction. Like, it's not actually meaningfully faster, which could be for a number of reasons, but unless we're doing something really horribly wrong here, which I don't think we are. Like, this could be because Chrome doesn't compile a very efficient version of that function, but that's gonna be really hard for us to do anything about if we can't look at the generated assembly, which I don't know if we can. So, okay. Getting back. So what I did was I removed the computation. In fact, let me put it back now that there was okay, none of this is like remotely right. So clearly our code super doesn't work. Like, nothing about our code works. And just looking at the code, I can't find anything that's obviously wrong. And so I suspect that it's a bug in the widening or narrowing or transposing or something like that. So the way we are going to debug this is we are going to write a function that prints a value yeah. So we're gonna say, hey, like, there's no way to print anything from WASM, but what you can do is you can print from JavaScript. So what you have to do is you have to say, well, let's say that there was a function with C mangling as things go. Let's say it's called debug print, and it takes, let's say, the name of the thing you want to print, and so that we don't have to deal with this, the length of the name, the data that you want to print, and data size. And let's write a macro that debug prints the name. This is including the zero terminator, so it's like this, and then the data, and then this size. Okay. And as a test, The issue is we have a mesh with like millions of vertices. We could switch to a simpler mesh, and in fact we probably should switch to a simpler mesh, but I don't want to do this right now, so let's just say debug count. And here we're gonna say we're gonna just print the first like 10 values, right? So let's first check if our widens worked. Now the issue is if I compile the code, and I did this before, which is why I know what I'm gonna run into, the extern doesn't really work, and there's probably a way to do this nicely, but I usually, I usually just hack this. So this is basically saying, hey, if there are symbols in the C code that you're compiling that aren't found, it's fine, just link it with that symbol being an external symbol, and then hope that JavaScript provides a version of that. Now if I'm gonna try to load this, we'll in the JavaScript environment, it'll say, well, I don't know what debug print is, which is not a problem because we can implement debug print. So it was name, size, I'm not sure what the naming convention is, data size. The pointers, which are name and data, are pointing into the WebAssembly memory heap, rather, which is this guy. And so this is where we get to the point where I don't actually know JavaScript. So I'll have to Google a few embarrassing things, such as convert ASCII character to string in JavaScript. No. Aha, this guy. String from char code. Cool. And you'll notice that I use var instead of let, and like in general, you shouldn't, how should I put it? You definitely shouldn't learn JavaScript by reading my JavaScript code or watching my streams, because hey, I'm not the best person in the world to teach people JavaScript. So when we are printing data, I kind of want, I guess I want hex output, hex format or something like this, I don't know. Okay, beautiful. All right, I don't know if this works, but we're gonna find out. Hey, so now we have a cool little debug print in JavaScript that we can use from our WASM, and it only prints the first 10 results. Now we are gonna quickly find out what's wrong. So this is our input data. 72710 is like the first normal, and then there's 3 more. 1 is the sign, right, of the z, and these guys are just the actual values. So after narrow operations, or widen rather, we are getting n0, which is the first normal, which is 72710, and then 6e, 77, 1a, 1, 75, 2d, 1, 0. So all of this looks to me like it's in a good shape. Now, let's print the results after transpose. I guess I'm gonna have to like debug plus, and then see, it's probably a bug in transpose. I mean, what else could be in, right? So this is pre-transpose, and this is post. Aha! So this part makes sense. This is 7.2 and 6e. This part doesn't, because it should be 77 and 75. So this is a great segue to talking about how transpose works. Looks kind of reasonable. I think this works. Let me look at the macro again quickly. 0, 1, 2, 3, 4. What? Okay. Cool. All right. And there was a typo in. All right, and now the code works. There was a typo in my adapting the code. Well, it doesn't work. It works better, I should say. It works as well as the code that disregards the Z component. Did I not restore that? Oh yeah, okay. So maybe this code just works now. All right, this looks correct to me. All right, so I think we fixed the bug. Are people interested in how transpose works? We don't have too much time left, so I could talk about this, or I could try to maybe look at the performance, although I'm not sure how yet. Well, I'll keep that for now, just in case we need this again. But if somebody wants to know how the transpose works, let me know and I can draw pretty pictures showing how it does. Alright, so the good news is our code works. The bad news is our code is slow. In fact, our code seems slower. Bit SIMD. Wait, what? Hold on. Oh, great. Yeah, our SIMD code is slower than our scalar code. So what this usually means is that we are hitting some, if I were to write this code with SSE, I mean, I don't know, but I'm pretty confident that it would be faster. I haven't measured this, right? It's hard to say things like that with certainty. And I can certainly, this code looks, the widening stuff is a bit complex. How do you do sign extension in SSE? maybe these are actually the problem, because like there's no way to implement them efficiently. I'm not sure. But like what I was saying is I could like implement that with SSE and then see if that's faster than scalar version. But we are doing extra work here with all of the transposes, right? Transposes by themselves aren't, they're like a significant cost here, but they're not too bad. They shouldn't be too bad. The widening stuff I'm not sure about. And maybe there's a better way to structure this code. Like this core of the computation is basically what it has to be, right? There's like 4 things, you do math on 4 things. But these outer bits, there is some inefficiency in transposing and then widening, and then narrowing. And like it's possible that definitely here we could just take the bytes of the output value and quickly get them into the correct arrangement without having to do this. But then I'm not sure how well it will compile towards the SSE. And I can't inspect the SSE output, unfortunately. Like what I was trying to do yesterday is I have V8 probably or something. No. Yeah, I have V8 and I was trying to use V8 to say, hey, can you please output the WASM? Oh, and now it works. Okay. This was anticlimactic. What? Hey, I was saying I tried this yesterday and it didn't work for some reason. Like it was refusing to output WASM code for. Oh boy. For the vectorized portion, and it couldn't. And I'm like, well, I guess I don't know what's going on in my code. Okay. So this is good news. This means we actually have the WASM output. So the way I found this is I was looking. The way I found the block of instructions is I was just looking for the square root, and I mean we do a square root, and here's our square root. So okay, all right, this is cool. Let me see what chat says. Coding scares me. Coding scares me too sometimes. Okay, so like to recap, right? Our code works, which is great. Our code is slow, which is not great. We don't know why our code is slow, which is also not great. Let's. Oh my. So these are the narrowing instructions, and this is our transpose, I think. But there is other stuff. I'm worried that what happens here is like this is our transpose or something, like this, right? And then yeah, okay, like transposing twice, we would pay a big cost for this. Damn it. And clearly, oh, so actually, can I like, hold on. No. All right, so. And let me So clearly our attempt to coerce Chrome into generating good transposes didn't work. So you can see it does a shuffle with 88, which is what we do as well, but we do 2 of them, and this thing does like way more than 2 of them. And there's more. What does this do? Oh, it's interesting. Huh, wait, what? So if I look at the start, let me first confirm that this is the loop that goes like to the right place. So like you can see that there's a bunch of SSC instructions, and then it compares something to something else, and then jumps somewhere, and then returns. So this should be our loop guard, right? So if I look at this, this is where our loop starts. Oh dear. Okay. Curious. Hold on. Okay, so there is a jump around a block of code with a call. I'm gonna hope that this is like some slow path for something that we don't care about and remove that. And I'm assuming this is the same thing. This Chrome code gen could be improved here, I think, because like it's probably better to move the slow path outside of the like to the end of the function or something. I've encountered similar things in my jet. But okay, so this is our loop. So there's some amount of stuff at the beginning, some compares that there should be like one compare at the very end. This stuff shouldn't really be here. Maybe it's some memory safety checks. I'm not sure. But then we actually see pretty efficient code. Curiously, well, so this is a 16-byte load, and then these are sign extensions. Oh, I'm guessing that there's no way in SSC to sign extend from like the upper half, so it has to shift the entire vector by 8 and then sign extend. But otherwise, I guess that's fine. Is there no way in SSC to sign extend 8-bit to 32-bit? So, clearly, there is a way to sign extend 8-bit integers directly into 32-bit integers. WASM doesn't allow for that, which is, unless I missed it, which is unfortunate. Sign extend. And there's no way to load for, like, my alternative implementation strategy was to load 4 8-bit integers like 4 times, and I was assuming that there is an instruction sign extends it to 32 bits directly. It doesn't look like that exists. But okay, so that's unfortunate, but I guess that's like we can't fix this obviously easily. So what this seems to do is it seems to shift the entire vector by 16 bits when it does 16 to 32 expansion. Yeah, because all of these instructions, they don't support extending from like the high bits, high bytes, whatever. So yeah, okay, all right, so that makes sense. So this is, if we look at our code, every instruction, like I guess this one or something, compiles to one instruction, and the high instructions compile to a line plus mov. So this is our sign extension stuff, where we align, shift twice, and then align, shift twice, align, shift twice. All right, so that's, I'll need to think about alternative implementation strategies because that's not fantastic. This is our transpose. So this is the integer to float instruction. And so this must be our transpose. Which compiled pretty well. I mean, I expected like 8 shuffles, and instead I see 4 shuffles, and then blend instructions for some reason, and then unpack instructions. But like, they're probably all the same cost, that's probably fine. And then this is our actual loop. This is a shift by 10. Why is there a shift by 10 in my code? After the comparison. Oh boy. What? What does... What? Wait, this is a floating point oh, this is... Oh. No, what? Right, this is all kind of concerning. I don't really understand what's happening here yet. Like, there's a max instruction that I meant to use here. There's also another max instruction which I didn't mean to use. So that probably... I need to like disassemble this whole thing somehow. What does this have? So this is using Chrome's instruction disassembly, I guess, in V8. Pretty sure VSQRT-PS only has 2 register arguments, like this, source and destination, and this seems to think it has 3. I'm assuming XMM0 is like not right, doesn't exist. So I'm assuming this is the actual correct disassembly. So then what seems to happen is before we do the square root, we do a max, but the max is computed, so this might be the case that the max instruction in WebAssembly doesn't directly map into the SSC max instruction in terms of NaN handling and whatnot, and the compiler generates pretty inefficient code, right, to like fix that, which is sad, but we can fix that better. Like, we don't need to use a max instruction here, so we'll change that. So after this we do square roots, mulad, this converts back into the integer space, then we do the sign flip, which is this, like compare for equality, and then I guess, and this is broken disassembly. I'm hoping people, I'm hoping at least, well, I guess Thomas is watching the stream. Thomas, if you get a chance, there seems to be a lot of bugs in the disassembly output here. Or not a lot, but like 2, right? The square root, which is a minor thing, but like this is clearly, I'm not sure which instruction this is, but clearly Chrome doesn't know about it, even though it synthesizes that. So anyway, oh, and then shift. Oh, whoa. Oh, this is a negate. Yeah, so my negate strategy needs to be different because my naive thing where I like negate and then bit select generates pretty terrible code. Not terrible, but like it feels like this could be 2 or 3 instructions and it's like not 2 or 3. But then the other thing is that the transpose plus, so this is the big problem as well. On the load path, transpose worked pretty well. Here, I'm not sure what's going on, but it's not good because why is there a comparison here? What is it? Is this narrowing? No, it can't be. Like this, I'm assuming is the narrowing, where it packs to the double word and then packs to the bytes. So that is good, but what predates that kind of is pretty not good. With ands, maybe some of these instructions are actually mixed in from here. I'm not sure what this comparison is doing here, basically. No, but it's after shuffles. This is all bewildering. All right, so let's see how much time we have. See if there are questions. No questions. So the only thing that I can think of is that we can try to like fix some of these code gen issues. And there's 2 ways to fix the code gen issues. One is to look at the disassembly in WASM, to look at disassembly in Chrome, and then to try to do something about that. Like we can look at V8 source code to see how V8 maps different things to what. The other way is to just blindly forge ahead and like try to fix something. And I'm not sure what's more appropriate here. I'm not an expert in V8 source code. I was trying to look up some things, but it's not always very clear to me like which part is the WASM code gen versus not. Oh yeah, so this says, oh great, yeah, okay, so that's actually, so like one of the problems here is that the max instruction intrinsic is actually not one instruction in SSE, it's like many, and yeah, okay, this is the code that does this. Instead of, oh, it's still you, oh dear, yeah, so, where is my comparison? Is this that? I'm still confused as to why there's 2 max instructions, even though I have 1. But so max here says it needs to compare and then it needs to fix non-behavior. So it's like mov CMP max or CMP. I'm wondering if maybe like the version of my code generator is different, so this code is different, or maybe there's extra instruction reordering applied after this. But okay, so this is clearly like bad. Like I don't want to use code like this. What I want to do instead is probably just compare and then mask zeros, because that's just like terrible. So that's an understood problem. So this problem is the problem that I don't understand basically. Like the transpose plus narrow seems to be very bad, and I don't know why. So let's see. Back assess. So these are the conversions, like the narrowing conversions, and they are all straightforward. Like that's that. So our real issue is shuffles. It's interesting that shuffles in one case are faster, much faster, and in another case they're pretty bad. Oh, is that because, well, Yeah, I don't know. I don't know off the top of my head what to do about this. It's weird that negate is also. Let's see. Why is there a sign shift by 31 is beyond me. It's not really how. Oh, maybe Chrome. What can sometimes happen in things like in code like this is that Chrome, sorry, not Chrome, like LLVM optimizes the code before before it gets to the actual like WASM engine, but the optimizations can sometimes ignore like what's efficient to do in that WASM engine and what's not. But okay, like I can't disassemble my code anymore because I'm using some instruction that's not supported by my current compiled version of WAPT. Let's try to see if I can like pull the version. And oh, and I have to fix the in the unfortunate turn of events, one instruction, and it's kind of my fault, was renamed, was like it changed its original bytecode from like 3, there's a gap between 2 and 4 here, to like C1 or something. I think it was this one. No, it's the one with immediate value, right? It's this one. And so there's a certain amount of surgery you have to do on the compilation tools to keep them working. All right. I'm getting kind of tired. I think what I'm gonna do is I'm gonna fix the sign problem, like the max problem, where max is just not good. And I'll have to raise. Well, there might be already an issue for this here. If not, I'm gonna have to raise an issue because it feels very odd. I mean, maybe it's just unavoidable, but it would be nice to have a max instruction that compiles into like, oh, yeah, okay. Marat already filed this. Yeah, this is basically the problem. 8 SSC2 instructions to load this WebAssembly instruction. Oh dear. Yeah. So basically I hit that exact problem, right? Like there's a min max instruction, it's slow on x86. It's fast on ARM, but it's slow on x86. So if you're trying to write code that's actually fast, 8 SSC instructions. Oh dear. Like it's not, and it's in fact it's even worse, potentially worse. Like I don't have a max here. I have a max with 0. I'm sure that you can do a max with 0 even if you handle nans correctly faster than like 8 instructions, but Chrome doesn't do constant analysis. All right. So my point was, I'm getting pretty tired. All right, this opcode isn't even in the, unless this is the actual, okay, out client debug. I'm not sure what this opcode is. It's clearly, oh, right, I can just look it up here. All right, cool. So the WABT thing, I guess, doesn't Yeah, doesn't know about the widening instructions, even though Chrome does, so I can't disassemble this anymore. Alright, so what I'm gonna do is I'm gonna fix the max problem, and then maybe the performance will be slightly better. But I think the bigger issue is this. This is just like unacceptably bad, and I don't understand right now why it's unacceptably bad, so I'd need to figure that out. And maybe if that gets fixed, this code can run faster. I kind of expected this code to not be this slow, I guess, in general, so I'm gonna have to do more profiling or something on this later. But for now, let's just do the simple thing. So let's fix max problem. Basically, we cannot use this instruction. This instruction is bad. Instead, what we're gonna do is we are going to compare yeah, we are gonna compare the thing to 0. So like ask when it's greater or equal than 0. And if it's greater or equal than 0, then it will return a mask of all ones, and otherwise it will return a mask of all zeros. And so if we AND the floating point value with the mask, we'll just automatically get effectively 0 if the thing was less than 0 and non-zero otherwise. We can also look at the sign bit, which is a shift. No, but then we have to still... Yeah, it's probably fastest to do this way. Pending like code gen playing nicely with that and stuff. So that's I think what we should write. Alright, it's appreciably faster. It's like basically as fast as Scalar code now, which is a great achievement. Maybe it's a touch faster than Scalar code. Let's confirm the assembly output. QRT. Alright, so now it compiles into like 2 instructions instead of, I don't even want to know. Marat says 8, so it's probably 8, but it was like really bad. This mob is completely extraneous. Chrome definitely needs to be better at compiling WASM. Unless I'm using the baseline. Let me try something. No lift off, I think it was called. Oh, I guess it says which engine it used. Yeah, turbofan. Okay. Chrome has, and the mob is still there, so that's not great, probably. Chrome has two WASM compilation pipelines: turbofan, which is like the one that produces good code, and liftoff, which is the one that produces bad code. But I don't think I'm using liftoff at all here, so it's fine. Yeah, so okay, so we fixed the max problem. Things got faster. I don't know what to do about this. Let's do a Q&A, and then maybe while we're doing Q&A, I'll come up with a brilliant idea that I'll just implement or not. I feel like I need a break and I need to think about this problem a bit because clearly, basically the issue is without Chrome's code gen problems, I was hoping that we would spend roughly the same amount of time doing like computations and shuffles and stuff like that. But because of one, the specific approach that I'm taking, two, the code gen issues that I'm having, it looks like the computation is actually like an insignificant portion of the workload, and the significant portion of the workload is the transposes, shuffles, narrows, widens, all of that, which maybe can be better. Maybe there is a better way for me to structure. Like, I can't change the memory layout of anything here, so it's tempting to like pre-transpose something and like stuff like that. I can't really do that for reasons I'm not going to explain right now. But maybe there's a way to change the approach that I'm taking, right? And like this, I'm sure can be different because I'm just taking values and I just have to kind of patch them into. In fact, that's a great idea. I kind of have to just patch them into the vector, and I don't even have to retranspose the whole thing. I think probably the right way to do this is to just throw this thing out completely and just say I have 16 bytes, 4 bytes effectively worth of results, and then I'm just gonna have to. Why am I not doing that? Oh hey, I'm gonna do this now. Alright, this is actually really simple. Let me do this first and then we'll do a Q&A, because maybe that's gonna be much better. Yeah, okay. So the issue is this, right? So why is Scalar code not suffering from this too much? Well, so the Scalar code has to write like 1 byte per loop iteration, so like 4 bytes for 4 normals. And here we are spending an excruciating amount of effort like making things, transposing them back from the column layout to the row layout, including narrows and transposes for all vectors. So like we are taking X, Y, Z, and W components and then repacking them back into what we started with. This is a reasonable approach if we had to recompute all of them, but we only have to recompute one. The thing though is, so if we look at this Z4, like actually what it is in the little endian format, which I'm not sure what the standard is in WASM on all of this stuff. Maybe there isn't one. So I'll have to think about whether this is safe from the endianness perspective. But like fundamentally, the thing I want is this. We started from X, Y, ZS, I'll call it that, which is like the psi and W, repeated 4 times. And then we computed, and this is what N4 is. So N4 is this repeated 4 times, right? And then I have ZR. ZR is the 8-bit extended to 32-bit, which maybe I wouldn't even need to do the exact same way if I did it like that, but like, so for all 4 components. So it happens to be the case that we had to do these transposes so that we can do things like compute 4 square roots at the same time. But once we're back into having computed one value, the one value looks like this, Z, and then I'm gonna put question marks here. What actually is, instead of the question marks, is either all zeros or all ones, depending on whether the value was positive or negative. And this is gonna be different for big endian versus little endian, which is what I'm not sure about. But fundamentally, this is what we have. And so all we need really is to replace these guys with like these guys. And this is not particularly challenging. There's a lot of ways to do that. We can do a byte shuffle, but byte shuffle probably will miscompile in some horrible way. I mean, we'll try doing a byte. Let's try doing a byte shuffle. Let's see what this does to us. I'm not sure how to deal with endianness, but let's assume little endian hardware. In which case the layout is exactly like this. And then let's just say that our resulting vector is just the WASM 128 shuffle. Shuffle. Oh, I see. So we need to shuffle N4 and ZR. And for the first normal, we are going to take the first byte from the original source, the second byte from the same source. Then the third byte is the z byte, and the z byte has to come from the first byte of the resulting vector. And I can just use a byte because of how sign extension works, the 32-bit component and the 8-bit component encoded inside it, they are the same on the byte level. So I can just take like one byte. So this is byte number 0, but I have to say 16, like let's say 16 plus 0, because it's the second vector. And so 3 for the W. And then let's just gonna do the rest. This might compile inefficiently for SSE. This is like the best way in WASM to do this, but this might have an inefficient code gen. But there's a way to do this efficiently with like a shift and mask. So we'll see, maybe that's what I'll do. So 4, 5, 16 plus 4, 6, 7, let me like 8, 9, 10, 11, 12, 13, 14, 15. So this is the case where like this shuffle is actually very readable, right? Sort of, because that's kind of anyway, like doesn't matter. So let's just try this. Hopefully that works, and then I don't need like any of this stuff. And so that, if that works, that hopefully is much better. It got slower. Maybe the code gen for one shuffle is so terribly bad, which could happen, that, oh dear, yeah, okay. So Chrome has to fix this problem. But because Chrome hasn't fixed this problem, this is a bad idea. This is like the perfect implementation of this. Looks exactly like I wrote like right now. The perfect WASM, it's not even perfect, like the good WASM compiler would take this stuff, put this in a constant section somewhere, and it's going to be one VP shove B. Instead, this pushes. Why does it even push? Oh my god. This is really bad. Like, this is like seriously really bad code gen. Because it also adjusts the stack pointer like in between inside the loop, which is gonna throw off all sorts of things. Alright. And like our code got slower, right? We replaced, let me copy this so that we have the original source and undo this. Right, so this is our original source with like 8 shuffles inside this guy plus 3 instructions here. We're replacing this with 1 instruction, and it's slower because the code gen is terrible. But okay, so the other way to do this is this. So we're not going to do it like this. Byte shuffle turbo perf on Chrome. This is the same problem because Chrome doesn't support constants. It's a problem. It has to be fixed. It affects everything. So the way that I suspect will work just fine. Oh, except that. Oh my god. Oh, I'm anticipating a fantastic problem that will happen just now. Oh, actually, maybe not. So what I want to do is this. Like, okay, fine, this didn't work. Chrome is stupid. What I can do, though, is I can transform this vector into a vector like this, right? Just shifting z in the right place, which is literally a shift. Which I can do with WASM I32 for something. Shift left. Right, so I can literally shift this. I have to shift this. I have to shift this left. That's counterintuitive because the value is moving to the right, but that's little endian. So I have to shift left by 16. So if I shift left ZR by 16, I will get Z byte in the right place. And then I just have to choose, like I have to select the right bytes for the right value. So the code that I want to write is this. Was v128 bit select. And then like the shifted value, the N4, which is the original value, and then the mask. And then the store, right? So, and then the mask is what I want is I want basically 0, 0, FF, 0 in all components. So what I'm worried about is that LLVM will compile this into a constant load that Chrome doesn't support. But let's see. Let us see. So I will try this. I will try splat and hope. Please work. Hope that it will like not. Oh, is this right? This is not right. This is right. Right. I don't know. Let's see. And it's still slow. Right. No. What? Why am I still seeing this terrible code gen? Oh, is it because... It's probably because LLVM tried to be really smart. Damn it. This is all frustrating. Like, I know exactly what I want to write. Basically, like, I know exactly the instructions that I want to synthesize. And I can't check this because widen doesn't disassemble, right? So I can't... All right, I don't know. So, okay, let's do it like this. I'm gonna hope that I can do this. All right, I'm gonna hope that I can do this. I don't know. No. Why does it generate this horror if it shouldn't be able to reason about this code? Or like... I don't know. me see what the chat has to say. Oh, good point. Thank you. We don't need wobd. So wobd doesn't work, or like objdump doesn't work because it doesn't know what widen is, and like I'm sure I can hack it in somehow, but I don't need this because I can just do this. Yes, thank you. Alright. Well, I might need to. Let me compile like one source file with the right settings. So this is the line. All right. What if I just do a metal VM? Does that do? Right, yeah, so now I only need one source file. Like I suspected a little VM. Okay. Oh, is that the... Oh, okay. Yeah, I suspected it, like, it's volatile. I'm not sure. Let's find the square root and then see. No. So with the volatile thingy, it's all great. Huh. Let me maybe right. Oh, is it the case maybe that this plat is just compiled? No. This assembly shuffles. It doesn't. Okay, let's do this again. Thank you for the suggestion. I do not need wobd. So let's do this. Wait, right, so this is all VM bitcode. What happens if I do this? Oh, nice. Wait. What am I even looking at? Did I not comment out? No, I did. Okay, let's do the volatile thing again. Like something in the toolchain is generating the code that I really didn't expect. Like it's generating weird shuffles. Oh, hold on. So this is the final conversion, right? Yeah, this is the conversion from like integer to from floating point to integer. After which. Oh no. Hold on. This is the actual bit select store. Maybe I'm just not reading this right. Maybe this shuffle. It's generated for a previous. Let me simplify this thing. this whole thing a bit briefly by saying, let's just not handle negative z values. Let's just always assume z is positive, because I think there is some conflation that I'm getting from. Right. So now with this mask workaround approach, it's good. Let's try to use that as a baseline and then go from there. Where's my make? So now the code. Now the code will not do the right thing, which is kind of hard to see, I guess. Well, you see, this is just the wrong val. Nah, hold on. Let me do the ground truth run again. Wherever that is. So disable SIMD, get the ground truth. Yeah, so like if you look at the right, if you compare this, like obviously there is large areas of the mesh where z is negative, and it's supposed to be negative, but we are now outputting always outputting positive value. But like whatever. So the good news is the performance is better. It's still bad, but it's much better. It's better than scalar code. Let me look at the code. So we broke the code for now. Like we. Oh. Wait. Hold on. Right. Again. Right, yes. So we broke the code, we don't do the right thing with the z sign. So let's look at what we have. All right, still don't like the result. What does it do? I feel like the truncate saturate is also doing something weird. Possibly. Let's see. Where's my blend? So this is. Oh dear, what? Wait. So this kind of looks like a bit select to me, except that this is odd. I'm not sure at this point how much I can trust this disassembly because of like bugs like this. So I'm not fully. I don't fully know. Like I'm worried that. Like I'm worried now that whenever it says rex.w, it actually says, hey, the disassembler doesn't actually handle some case correctly when there's like a rex prefix instruction. Because like if this said mov, I mean even if it said mov, it's 31. Why does it shift by 31 to the left? Or what does it shift by 31 to the left? All right. This is the bit select pretty clearly, I think. Or at least it looks like a bit select to me. because that's like a constant offset, and that's like a non-constant offset, and if RBX is the WebAssembly heap or some such, then yeah. So this is a bit select, which, by the way, is also surprising, because I would expect Chrome to use blend instruction here, which is like faster. But then the shift left is the same shift left. I'm just weirded out by the fact that it should shift by 16, and nowhere here it says 16, and in fact this guy comes from this. I feel like this is just broken, disassembly, because, or maybe not. I guess RDI is 16 here. Oh, of course. Oh my. So shift left is not efficient here, right? Because shift left by 16. Chrome says, well, the WebAssembly spec says that shifts by values that are larger than 31. Wait, why 31? Oh, right, yes, 31, of course. Have to, okay, the assembly is correct. Basically, this ends the value with a constant, because if you shift by like 35, WebAssembly spec says, well, it's actually a shift by 3. The value here is constant. V8 doesn't know that, so it ends. Okay, all right. So that's at least the code that makes sense. This is a bit odd as well. This says to me that the basically this says to me that the truncate saturate stuff, like the thing that converts from floating point to integer, this is kind of what it corresponds to, what I have highlighted on the selection. And it probably has something to do with like NaN handling or some such, which also is not great, because I mean, like, I don't need that, right? But okay, at least the code is, oh, but we didn't handle the sign. But okay, the code is less slow now. So this is actually like pretty reasonable, sort of. If some of these small issues here get cleaned up, like this should be one instruction, this should be one instruction. So if that gets fixed, then it would be pretty close to the assembly that I wanted to have in the first place. But okay, so this was a thing that I would want to do anyhow. Thomas said that little endian is basically guaranteed, which is good. This means that this code is correct. I don't know if I need the volatile hack or not, but like whatever. All right, so I am tired now. It's been like more than 2.5 hours. So let's end the stream here. The short story is we have code that works. Right. If I close this, it is not fast. We're hitting a weird mix of code gen issues. This will get some trial and error to sort through. Like the value, I'm tabbing between SIMD and Scala versions, like the result is exactly the same. So the code works correctly. It is not fast. We found a couple of issues in the performance area, but it's really, really easy to accidentally trigger like poor code gen in Chrome. Like this is, I think, if I update this right now, yeah, like this stuff is just like really bad. And this is because of a complex combination between like LLVM optimizes some code and then Chrome generates some code from that, and they're not always aware of each other. So like I should never see RSP adjustments in my inner loop. Sorry, this is broken. So I will. I'll need to look into the whole thing again after I kind of take a walk and stuff. Like, I'm tired. The I need to think about, like, if I can make the sign. So I'm pretty happy with this part. This part is great. Like, I don't actually need to do this whole thing. It would be nice if the shuffle, single instruction shuffle, just worked without these shifts. But it doesn't look like Chrome supports it right now optimally. But also, like, I'm hitting this similar issue right now for other reasons. So that needs some looking into. And I hit the max issue. There is already an issue filed with the proposal for alternative max instructions. So if we had that, I could use the max here. Although in this specific case, I don't actually mind. Like, I mean, greater or equal plus end. I think it compiles pretty much into the exact same thing, like this. I think. Hold on. Yeah, like this is my square. This is my square root adjustments. This instruction shouldn't be here, as in it moves from 2 to 12 and then reads from 12 in here. So I'm assuming this is just a code gen issue on Chrome side, but otherwise, like, I mean, I don't really care about max too much, now that I know that I should never use that though. So, like, there's a bit of a food gun there. Happy with all of this stuff. Reasonably happy with the load. This surprisingly compiled just fine. Like, right? Except that, of course, it's still a bunch of instructions. So I think my homework is try to figure out if this path can be simplified conceptually, not just like get better code generation from the same WASM instructions, but more like reworking this so that it needs less, so that I need to do less work, right? Which is complicated a bit by the fact that I need to transpose, but also I need to widen. And I need to widen from 8 to 32, and WASM doesn't support that natively. So that needs some thought. And also the sign stuff. I suspect that this horror is now coming from here somehow, or from combination of this and this, or like, I don't know. I'll need to look into that. But I'm tired. Does anybody have like a question that I should ask? Yeah, I can definitely file V8 bugs on the code gen issues. I think to summarize, so there's a disassembly issue in V8, which makes it hard for me to read some of this code. The shuffle code gen in this fallback case where there's a shuffle with constant byte arguments is really bad. This should never be like that. And there's a few paper cuts, right? Like this shift by a constant shouldn't have an end, and there was something like this extra mov, stuff like that. But these are much less severe. Oh, and like I never quite figured out what the hell was going on in the store path, like with the transpose and narrow. Like, it seemed like it should have been relatively fine, but it wasn't. But also this is a bad idea anyway, so like, I mean, I shouldn't have done this, so that's fine. Wait. Hold on. Hold on. Yeah, right, okay. And I don't understand yet what happens here, but something really bad does. So once I do, I'll need to file an issue on it as well. Alright, hopefully this was mildly entertaining, interesting. I don't know, you got to watch me suffer a bit, but it was almost worth it. My only, like, we didn't get to a place yet when we had a vector path that was noticeably faster than the scalar path, which is not great. But I'm gonna think about this a bit more, and I suspect that there is a solution here. It's not as straightforward as I thought it would be. But hey, at least the code works. Oh, I need to file a WAPT issue for supporting. I mean, I'm sure that it'll get taken off somehow, but it doesn't support widening, which in the disassembly output, which was a problem. There's probably already like an issue on this. No? Huh. Huh. Okay. That is good to know. I will file that. Basically, these guys are not supported. Okay. I will file that. All right. Any last minute questions? Roblox post-processing effects questions off topic. We're working on some stuff, but off topic. Not answering that. All right. As usual, this stream, the recording of the stream will be on YouTube, so that's good. And I'll also, I'll have to work a bit more on this optimization problems, like codegen problems. And at some point, something will actually land into my GitHub repository for meshoptimizer. But right now it's not quite in a state, I guess, where I just want to submit this. Oh, plus I have to, there's actually like 4 variants of this loop, right? There's a minor variant here where the source is 16-bit integers, which, I mean, it's roughly the same, it just affects the load and store effectively. So I'd have to, this gets simpler because I have to load like 2 16-byte vectors and then widen them, and then the rest is exactly the same, and then the store gets affected, so I have to think about that. And then there's also 2 more loops that are basically the same, except that they reconstruct the 4th component out of the first 3, but that's basically identical because you just have to like do this for the Z component, and then this is W and things like that. So not much different. This is like the hardest part, and once I iron out the codegen issues, the rest will be easy. All right. Thank you for joining me on this journey. This was my first time using like floating point WASM instruction stuff, as I mentioned before, and also this is my first time I actually but like I figured out how to do the actual disassembly output from V8 like yesterday when I was thinking what I'm gonna do, thinking about what I'm gonna do on stream. So that's gonna be very useful for me in the future because the previous optimization that I've done was more blind, where I'm like looking at V8 source code to try to figure out what might be fast and might be slow. This is much more direct and helpful. So that's good. All right. Thank you, and have a good rest of the day. Oh, whatever. Oh, common high-level operations. Yeah, so shuffles, I was thinking about this. There's actually a proposal, right, on the CMD spec that probably will not go through, I'm guessing, because what was it, like other shuffle variants? Oh yeah, like add other shuffles back. And so there is some code size considerations, right, in terms of like 32-bit shuffles and things like that, but they might not be important enough to fix. However, yeah, like so if you look at, okay, if you look at my shuffle helpers, they come in 2 groups. Let me split them. So the first group is probably not like that meaningful, because the first group is like, hey, here's the shuffles that are the exact equivalents of the SSE shuffles. And the reason why I need them is twofold. One is a lot of the WASM code that I was working with, CMD code before, was converted from SSE. This was like the most straightforward path. So if I have unpack low in my SSE code, I don't want to like write out the full shuffle thing. So that's one reason. Another reason is that these paths match directly to their SSE equivalents in Chrome's codegen. So this is like, if I'm writing this, I can be reasonably certain, short of LLVM optimizations, that I'm not gonna go into this really slow path where there's like this pshov b from stack with pushes on this, right? So these I'm not sure about, right? Maybe they're not like worthwhile. These I feel like might be meaningful because the thing I had to write today is basically, well, Wasm V816 shuffle, except that it's not V816, it's like V32.4. So like the semantics are exactly, well, sort of modulo the SSC weirdness. But like there's a generic version of this macro, right, that is just V816 shuffle, but working on 4 32-bit indices, 4 indices into a 32-bit vector instead of 16 indices into a byte vector. So that I feel is useful. You know, like things like that, they save typing. Maybe that's not very useful. So I would say that these two I feel like are very convenient. Maybe there should be, maybe this shouldn't be called Swizzle. I'm not sure. I forget what the name conventions are. But maybe there should be a variance of the shuffle stuff that are basically V16x8 and V32x4 and maybe V64x2, although I personally didn't need them much. Just even though the spec doesn't support that in the sense that it's still a byte shuffle underneath it. So yeah, maybe. I wasn't sure. I was just mostly making these as I went through the code. So you see they are prefixed with X, Wasm X, so that I can differentiate them. But yeah, possibly. Definitely some of these could be useful to have in the 128 like header in script. All right, thank you everyone. The stream will be on YouTube, and if I end up making this code better in the future, I'll think about if I should do another stream or not. Bye.